Hello, my name is Ann-Christine Wörl and I would like to present our paper Initialization, Noise and Image Gradients and Saliency Maps. In this paper, we show that gradient-based saliency methods contain significant noise caused by the deep network initialization and training. To get rid of these artifacts, we examine a simple way to remove the noise by performing marginalization. Our work is motivated by contemporary research that uses classification to gain insights into data. Here, the goal is not so much to understand how the classifier works, but to understand the data itself. For instance, existing literature includes studies where CNN classifier can predict the effectiveness of a specific treatment for tumor tissues. By applying an attribution method to the classifier, we can identify the features of the tumor that are associated with the success of different treatments. We want to caution the reader to draw conclusions about the nature of the phenomenon observed from a single model instance, since even sophisticated approaches such as SHAP or LIME generate qualitatively different attributions. Now let's dive into details.
So formally, our setup would be as follows. F is a deep network, theta are its parameters after training, x is an input image, and y are the output logits for the classifier. And then there's a saliency method S that explains what f actually reacts to for a given input x. The issue is, of course, that this will not only unveil effects intrinsic to the data, but it might also be affected by extrinsic effects, such as differently behaving classifiers, or different behaviors of saliency methods. There might be different training schemes or hyperparameter choices that also affect what is unveiled. Then the initialization of the parameters before the training might have an effect, and maybe even aspects of curating the data itself. The main contribution inside of our paper is that noise from initialization and random choices of training batches already lead to considerable variability. And unlike the other effects, this variability is, at least conceptually, easy to remove by simple stochastic integration over the initialization distribution. So here's some results that we got. First, we look at image gradients. That means we just take the gradients of the logits by the input image pixels. This is a very simple method for attribution. If you use a well-performing standard architecture, then the function values f of x will vary very little on the whole data distribution, because if that would vary a lot, then it wouldn't generalize. However, the gradients are rather unstable and noise can be much larger than the actual signal. So here are some example images. On first watching, you might, for example, look at the images of the dogs. If we switch between different gradient maps slowly, so these are 30 different initializations, we can see that there's quite some strong variation. And if we speed up the animation, we can also see in the flickering how the classifier actually reacts to different subsets of the dog faces, and then there's also some overlay noise that reacts to background features that are not obviously associated with the class. By marginalizing over the initial weight distribution, we can reduce noise quite a bit, and it drops significantly below the signal level. Noisy gradients are not so unexpected. For example, if you think of a perfect dog image, and it should have very small gradients anyways, because it's already the perfect dog. So one way to avoid this feature saturation problem is by using integrated gradients, where gradients are accumulated on a path from a neutral image to the actual image, and thereby we are counting for all the hills to climb up on, which actually might contain the important features. As you can see in these results, this reduces initialization noise, but attribution still fluctuates between different image portions. Another technique is to integrate, in this case in addition to the previous integration, over regions in image space so that we avoid local differentiation, which is ill-posed. Integrating, we remove this source of noise. And as you can see in the examples, it helps, there's less noise, but there's still quite some fluctuation that could suggest quite different attributions, and that is for the same network, just initialized differently. So here's some results for DeepLIFT, another popular method, and again we see similar problems. This example is GradCAM at an intermediate layer. It's picking up features in the middle of a ResNet. GradCAM of an intermediate layer varies actually quite a bit, and it's not a reliable indicator of what the network reacts to. Most popular are top-level GradCAMs. So we look at the top-level pooling layer and then apply the final classifier only to these pixels in the pooling layer. In this case, this really varies the least, and the signal finally actually exceeds the noise level. Nonetheless, there can be still results for different initializations that would suggest that we attribute the effect to different regions of the image. The two most popular attribution techniques, LIME and SHAP, show large variability. This might be due to their ability to explain particularly well how the classifier works, and the classifier works quite differently when initialized differently. Finally, we also apply marginalization to gradients in DeepDream, which means optimizing an image to produce a strong output for a certain class. The visual improvement underscores the strong influence of initialization noise, although removing that alone does not yield perfect features, as one would expect. So the main conclusion of our paper is to caution the reader with respect to interpreting attribution results when explaining data rather than the classifier. As we can see, the network initialization already leads to quite some strong variability. We also show in the paper to remove this source of noise, but we will also suspect that there's more variability hidden in other external factors such as the architecture itself. Thanks for your attention.